sorry. Do you want me to ask you next time to give me the exercise as a sheet so that you're forced to do it?
The quality of topological interpreter, the logarithm of spectral radius is very simple corollary from Frobenius theorem.
Okay. Do you want to concretely explain this on at the blackboard? Can you explain to?
I'm not very sure, but
American that will help you. No, I think I agree with your sentence. So maybe you can recall what is Frobenius theorem. There are several variants of the theorem, and we are using which one?
Suppose we have matrix M, and all its entries are positive. Then it has the biggest by of the absolute value, eigenvalue is positive first.
There exists one there.
So this is real.
So on the right, the definition of the spectral radius. The spectral radius is the maximal absolute value of an eigenvalue, but in general, eigenvalues of a matrix can be complex.
And then, if I'm not mistaken, the corresponding
yes, but so maybe you want to say that this, you said it, but you want to write it, that this is also in the spectrum. This is
yes,
because this is always true. And the fact that this is, you can replace R.
Yes, I understand. Yes. And then belongs to spectrum.
And the fact that this is also an eigenvalue is a specific case.
And the second, if I'm not mistaken, there exists the corresponding eigenvectors from the first. There exist eigenvectors such that all its entries are positive, and this eigenvector corresponds to our eigenvalue number.
AG equals number
and if I'm not mistaken, it is the only vector. I mean,
surely it can multiply by positive constant.
Of course.
Yes.
And
so it's the only vector up to multiplication.
Up to multiplication, and of course, I mean, any other, no other eigenvalue have eigenvector with such property. I can write this, but up to multiplication.
Yes, okay. But do you want to use it? Because are you using this property after that for the entropy?
I want to project the vector of all entries, which consists on all 1, 2, 3, and I want to write it in basis.
Okay.
I'm not sure. Maybe not
okay.
needed.
So
this is from Frobenius theorem.
okay.
And we had, we discussed that we have the following equality. Our topological entropy equals to logarithm of by n.
So, yes, in which setting are you? What's the setting? What is M? What is X?
X is our space of not forbidden sequences, allowed sequences.
And M?
M is our matrix M, and
But how they are linked? Maybe you can have a little picture for everyone to see. Maybe you can draw an example so that everyone remembers what is the link between a matrix and
okay, we have the definition of topological entropy that it is all possible and words, and we have the equality that all possible words equals to the sum for all E in G.
So, is it true for every X, for every subshift X? When is it true?
We discussed that we don't have dead end, and I don't know how to say it in English. Источники, sources, and targets.
But can someone? So for every subshift X, we
finite type, or
finite.
of course, for all it is. We consider only a Markov, a topological Markov shift.
Okay, so we are in the set of path alpha graph.
Of course, yes.
So, for example, this. And you have a matrix.
Matrix that corresponds to this graph.
Okay. Which gives the edges for every edge. So it's not even every subshift of finite type. Up to conjugacy, it's every subshift of finite type. We saw that we could all represent them like this. But directly, you're dealing with edge subshift. Yes. Okay.
And
so well, your capital M is the same as your small m. Okay. No, it's not M.
I'm not M, yes, K.
No?
I will use here K,
Okay.
and to have N.
This N is this N. Okay. So here N equals 4. Yes. Okay. So how do you?
So then the number of all possible words is equal to I don't know how we will prove it, but if I'm not mistaken, it is equal to the following scalar product, inner product, where E is the vector of all points.
Yes.
I'm not mistaken, it is true.
So, not exactly because you,
That's okay.
And I want to project this vector to our eigenvector. But maybe...
yeah, so how do you, what do you mean project?
I want to... I want to have an eigenbasis, but it is not necessary that it is exists. I want to write this vector E using...
But you don't care about what happens in the non-eigenspace. You care about what happens in the eigenspace. So maybe
we can...
So what does it mean that it's the eigenvector? You wrote it, and V equals lambda V. Yes, for this particular V.
Yes. But...
So you don't know about the general vectors, but what you know is that V, what you know about V, which is very important, it's positive, yes.
It's positive, yes. And
so you can consider, for example,
projection on this vector.
Okay, so just some kind of intuition. Entropy is something about exponential growth, and it avoids many small modifications.
Yes.
Don't see them in the entropy. So usually when you deal with entropy, it's enough to deal with inequalities. Very often, maybe you can show both inequalities independently. And it's nice to have inequality, to be able to deal with inequalities, because when you have a positive vector, it has a minimal entry and maximum entry, which are positive. See what I mean? So, lambda V is
maybe I'm mistaken. We can write our vector E by as a sum of its projection to our vector V, and its orthogonal.
Yes, but what are you going to do on the non-eigenspace? Or maybe, okay, maybe you can do it. Yes, maybe it will be more or less the same as take the minimum
D by orthogonal. And if we write this equal to
AB or 2AB?
no, 2, because these vectors are orthogonal. If we have here V, we can equal to logarithm is qualitative. And maybe we'll have something nice.
Yes, I think it works because you know that on the orthogonal it will not grow, the norm will not grow more than lambda to the k, because it has a smaller eigenvalue.
Actually, we should prove it.
And we can divide by lambda k here. Divide by lambda. By k. Yes. And
Which is bounded.
Was something small.
Something bounded.
Yes. And this one in the denominator is bounded, simply bounded. So this one is one over k. Not one.
Yeah.
So our limit is already.
Sorry, what is this symbol? I have never seen this. No, just explain it. When you O with equal underneath?
This one has the same order
No, I understood the proof.
as 1 over k.
Yes, I understand the proof.
I denoted by this one. Oh, I don't know. In this it's written by big O.
Ah, this is by big O. Okay. Big O doesn't mean it has the same order. It means it's bounded.
Yes, it's bounded. We have two constants that.
No, just one. If you have two constants, it's theta.
I will not insist. Then we have converse probability.
Okay, but so it's a pity that you erased what you have written before, because what was your assumption on the matrix?
Because there exists some degree of this matrix such that all its entries are bigger than zero, strictly bigger than zero.
And this is always true?
No, of course not. If we have identity matrix, we will not.
Okay, so
Disconnected components number of.
So this is the definition. It's not even about. It's even stronger than strongly connected. It's called primitive. So primitive means, yes, thank you. Primitive, the primitive matrix or the primitive graph. Sometimes it's called an aperiodic graph, but I don't want to use this word too much because I use it later in another meaning. Primitive matrix for all ij, no, there it is. N.
No, K. Because N is the number of points.
Okay. Such that for all ij, and ij to n to the k, the entry ij is positive. And an irreducible matrix is for all ij there is this k. Okay, it's different. So do you understand what irreducible represents? In terms of graph, for example, I have the matrix of a graph.
Strongly connected.
Yes, irreducible is exactly strongly connected graph. Because remember that this means there is a path of length k from vertex I to vertex j. If it's non-zero, it means there is this is the number of paths of length k from vertex I to vertex j. So all vertices, all pairs of vertices are linked in both directions. And the other, I don't know if you see what it means.
All classes, we have such theory like every two vertices have a path from one to another with length no more than k.
Yes. So in particular, it's strongly connected, but it's more than this. So for example, this one, is it primitive? This graph? So first, if I ask this, first you look if it's strongly connected.
Yes.
Because if it were, if it weren't, then maybe it would be.
Yeah, so this case that's one.
From 4 to 3.
I forgot that one case. 3.
What's the question?
Is it primitive? But so you think that it is?
Yeah.
Okay. So there is a path. I think 4 is it? I think.
One, 3.
Have a look.
Well, I would say a bad number if I try to say the number, but what I can say for sure is that it exists because you have a loop. You have a loop. So it means if I want to go from some vertex to another vertex, if it's strongly connected, there is a path, and there is also a path to the loop, and the loop allows me to wait. Yes, sorry, I can wait.
Yes,
That's what you were saying. And more generally, if there is no loop, maybe there is no loop, but it's still primitive. Do you have a feeling of the property that is being called? Yes. It's about the length of the cycles. If I take many cycles, for example, if I take this graph, for example. You think it's primitive? Do you think it's primitive?
Either we should have the greatest common divisor of all groups should be 1.
Of all cycles, yes.
Cycle.
Usually I use loop for the cycles of length 1. Yes, exactly. So irreducible corresponds to this property. For example, if I have a 3 cycle here, it's okay. Because by Bézout's theorem, I know that I can always find a path of sufficiently long length because these 2 prime numbers allow me to a delay of 1 if I use them in a certain number of times. If you're not convinced, maybe it's a good exercise at home, and it's very easy. So that's fully connected. So
About the graph in the middle, isn't primitive, okay?
no, it's not.
Okay.
Because the greatest common divisor is 2. So if you want to join, say, this one with itself, you will always need an even number of steps. And if you want to join this one with this, you will always need an odd number. So dynamically, this has an interpretation also. So remember that there was an exercise. I'm opening a parenthesis and we'll go back to the entropy later, but there was an exercise on interpreting transitivity, topological transitivity of the subsheet in terms of the graph.
It's strong color.
So it's the same as, yes, exactly. So, we gave a definition of transitivity as existence of a dense orbit. Here I will give another definition, which is equivalent for all the subsheets. It's equivalent for all dynamical systems which are homomorphisms. Sometimes when you deal with things which are not reversible and which have isolated points, there could be a difference between the 2 definitions. But a very common definition is this one: for all U, V, open, non-empty subset of X, there exists N, such that sigma to the N of U intersects V. dynamical system, it means that imagine you have a space where you have a set map here, which you apply and you see orbits of points. Then this transitivity notion means that if I take even a very small open set here, and another one here, maybe two small open sets, then there will always be an orbit from one to the other. So it's kind of a indecomposability property of the dynamical system. I cannot get rid of totally one open set, which is non-empty, without breaking some orbits. So, yes. Do you have an idea of what it means? So,
We demand that n is always bigger than 0, or it should,
yes.
it can be negative.
Yes. There are several variants, and here they are equivalent
Yes.
in our context.
We can just check.
There are cases of dynamical systems a bit weird where they are not equivalent, so maybe you know. But do you understand why this property is equivalent to strong connectedness of the graph? So can you explain with your words?
If it's transitive, then we have the surface, and for example, for each E and G, we can find E.
For each what? Sorry?
For each two vertices, we can find somewhere E and somewhere G, so we have a path from one to another. And then somewhere we have E once more, so that we have a path to, I don't know, to another direction.
So, sorry, which
Or we can say
side are you?
we can just say that we only one vertex. Vertex is an open subset, so that
Yes.
we can choose the definition and.
Yes. Okay. So you're talking about this arrow from here to here.
Yeah.
So if we suppose this, then you know that the
One point is
vertex corresponds to,
an open non-empty set.
in some sense, yes, because you can, if you are in a vertex subshift, it's obvious that the set of configurations which are at this vertex at time 0 is exactly the cylinder where you force this letter in the middle. And if you want the edge subshift, then the set of configuration that are at this vertex at time 0 is the union of all incoming, of the cylinders corresponding to all incoming edge. For the edge subshift, it doesn't mean anything to be at this vertex at time 0. But if you say at time 0 I'm in either of these edges that go to vertex 1, then this is an open subset, which is non-empty. And if you want another vertex, you say that you can go to an open subset which corresponds to the set of edges that come from this vertex, for instance. And this means there is an orbit, which means there is an infinite path which goes from one to the other. So there is a finite path which goes from one to the other. And conversely, if the graph is strongly connected,
then, I don't know, for example, we can build a dense orbit, because first of all, we can numerate all vertices from 1 to n, and then, okay, we have the first vertex, then we have a path to the second, then to the third, and then to the n. And then we want to have all paths with length 2. So we go to the, we enumerate all paths with length 2, and we go to the first one, to the second one, and so on. And so on.
So we did all open.
Yeah. So we need to have all finite combinations in our work.
So here you are, no, it's good. You proved it with the definition I gave last time, but with this one it's even easier, I think, because if you have an open, if you can only, if you want, it's enough to prove this for cylinder sets because it's a base, and even for single cylinders, because by definition the product topology is based on the symbols on the cylinders A for A in A. Okay, index I, which is the set of configuration such that A equals A. But then if I want to join
But it is not sufficient if we prove that our trajectory needed all one index cylinders. It's not sufficient to prove that.
It's a question or it's
a question and a statement. Hypothesis. Because
in some sense,
we cannot.
the rest of the proof is hidden in the fact that this is equivalent to dense orbit.
Yes, but it's simple to prove this because if we have the dense orbit, so
we can visit all cylinders. We can.
Yeah.
Because we can represent all finite work in our
Yes,
orbit.
dense orbit is strictly, what I'm saying is that proving that there is a dense orbit is harder than this. Once you have the dense orbit, this is obvious. But if you just wanted to prove this, it's a little simpler. Because you can put on the base and then it's exactly it will be exactly how that you can link any two edges. But it's true that I'm hiding half of the proof that you had to do, which is the equivalence between these two definitions, which is some kind of induction. So it was not useless what you did. Yes. So and now. One question you didn't have to do, but you have to do now. If I have a primitive graph, can you imagine more or less what kind of dynamical property is equivalent to having a primitive graph? It has something to do with this also. It's called mixing, topological mixing. So sometimes you say you find equivalent notions from the strictly ergodic theory, which uses measure theory. And here I will always talk I won't really have time to speak a lot about measures during the course, so I will probably talk about topological variance.
I'm sorry. But if we have irreducible matrix, it implies that it is primitive. Because if we will have one that the k degree of matrix is not zero everywhere, all its entries are positive, then the next degree will be...
No, look at this graph in the middle. It's irresistible, but it's not primitive.
You are in the wrong direction. This is irreducible and not primitive.
No, it's written on the blackboard that irreducible matrix that there is this case that all entries are positive.
No.
But if we...
No, this is primitive.
Primitive, but under this irreducible matrix,
For all entries,
there exists, yes, but
That's what you said.
the next, for k plus 1, the degree will be all, the matrix will be
no,
all.
you can lose some ones because you don't have loops. So for example, here in this matrix, this is the matrix of this graph, and if I do the power 2, so for power 2, I will get this graph, I think. So the graph of length 2 paths, and this one is isolated, you see. This one, with the length 2 paths, it must come back to itself. It is obliged to come back to itself.
But
the
second degree of this matrix is also
1,
0.
0.
So this matrix is also non-primitive. This matrix is also non-primitive.
It's even non-irreducible.
Excuse me. I missed it.
Sorry? Yes. Thank you.
I'm sorry. I thought that the first there is this case that for.
No, I repeated. I showed you. I don't know how to say it. We showed you. Like it's in the opposition.
But if we have first that there is this case that.
Then you have exactly this definition of. Primitive is exactly the reverse of that.
I thought primitive for every case. I mixed.
So, but it's a good remark. If you have primitive matrix,
then for
every big k,
yes,
for every k prime which is greater than this k,
you
will have also that all entries are positive. Why?
Because if we couldn't obtain matrices with all positive entries. If we have, it means that we have a row of zeros in our initial matrix.
But there is a very simple explanation to being able to class it.
Because we can go
In the graph.
somewhere, and then we have a path with
Yes.
no more than k.
Yes, exactly. With exactly k.
Yes.
So if you want to have k. So it's a good remark because it's linked to what I will write here, which is that. So now that I've said that it's linked to what I will write here.
About mixing.
Yes. Can you imagine the definition of mixing?
For every n bigger than
Exactly.
some.
So for all uv blah 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 non-empty open subset of X, there exists n such that for all m greater than n, there is an orbit of length n which intersect, which links U to V. So I think with the discussion we've just had, I think you can get quite an intuition why this is equivalent to having a primitive graph. And if you don't have, you think really of this graph. So you can link every open set to another another open set, but not with every sufficiently large path. So now let's go back to P.Guillon. So you used the variant of the theorem for primitive matrices. But actually, the points that you wrote are also true for irreducible matrices. So what you wrote on the blackboard, everything is true if we assume that our matrix is even irreducible. So many points of the P.Guillon theorem are not true if we say irreducible, but you wrote only the two interesting points for us, which is the existence of this positive dominating eigenvalue and the existence of a positive eigenvector, and this is true. Let's say for irreducible edge subshift, there could be and this corresponds to the strongly connected graphs. What are we going to do for general graphs? So what can we do if we have something which works for strongly connected graphs, and we want to do something for graphs in general?
Examples.
Exactly. So non-strongly connected graph, for example, would look like, I don't know, something like this. So you have strongly connected components. There is one here, there is one here, and there is one here. Okay? And maybe let's add another one here. Okay. Now, we want to count the number of, maybe I will just give an intuition on this and not do it very formally because time is going. We want to count the number of paths of length n. We want to count them approximately. What does a path of length? What does a path in this graph look like? in terms of, we are talking about strongly connected components. So what can we say?
We can,
Our discrete time is M or Z?
Z.
Z.
That's a good question.
if it goes from one component to another, it should come,
Shouldn't come back.
yeah.
That's a good point. So, for example, if I look at the edges which link two components, I have 4 here. I know that each of these edges, I cannot take them twice in one path. And so, for each path, there are at most 4 positions where I will change connect components. Actually, I even know that there are fewer of them, because if I arrange the connected component correctly, I see that the maximum is 2 changes of components in the path. But we don't care, we just want a bound. So there are at most 4 positions where you change a strongly connected component. And 4 is very small with respect to n, which goes to infinity. So if I take a path of length n, maybe I can take 4 positions, and in between these 4 positions, what happens?
It's just passes in a component.
Yes. So I can apply the previous result to some blocks of the matrix. So, because strongly connected components correspond to blocks of the matrix. Actually, you can even write your matrix as a triangular, a block triangular. And each block is irreducible. Can you see this or not? I just rearrange my strongly connected component. I rearrange my vertices so that all the first ones correspond to the strongly connected component, which is which has no input edge. The last ones are a strongly connected component which has no output edge, and then I rearrange them so that the edges can go only to a strongly connected component that I haven't seen yet. Okay, it's just another way to see it. But then for this kind of matrix, the dominating eigenvalue is the maximal of the P.Guillon eigenvalue in each component. Only connected component, or each block. So, and so to prove this, it's really enough to say what we have just said, that each path can be decomposed in at most 4 pieces, and inside each piece, the number of possible subwords will grow at most like a log of the corresponding zero eigenvalue of the blocks, but it's less than the log of the biggest of this number. And then you add up, because the sum of these 4 or 5 lengths of subwords should be n, so it adds up correctly because the number of words, the total number of words is at most a product of the number of subwords that you can get. And this gives you an inequality, h of x is less than log of lambda. And in the opposite side, the converse, it's much simpler. You just say that the entropy of a subsystem is less than or equal to the entropy of the subsystem. So, if I always stay in the biggest, maybe the biggest is not the first one, but here the biggest is this one, because all other ones have entropy 0. This is a cycle, this is a cycle, this is a cycle, and here there is some entropy because I can choose, each time I do this, I can choose between looping or there is entropy golden ratio like last time. And but if I decide to ignore all of this, the set of configurations that always stay in this strongly connected component already has this entropy, so it gives me the other inequality. If you want, I think you get the intuition. For the first inequality, you have to write it. There is no difficulty. You have to write the decomposition and the inequalities that it gives you, and it's direct. So we really get this. Okay. Yes. So all of this is to tell you that when you have subsheets of finite type in dimension 1, you can represent them as graphs, and you have many properties to be read on the graph. So, by the way, the first property you want to know is whether the system is empty or not. We'll see, but we'll see that in the following parts of the course that it's not as silly as it seems. Here, if I give you a list of forbidden patterns, for example, 3, maybe not 3, let's take binary. 1, 1, 1, 0, and 0, 1, and 1, 1. How do you do to tell me that there is at least one configuration which avoids all of these patterns? What's the general method? I think you have more or less all ingredients to come up with a general method. So what do you know so far about your subsheets of finite type?
Subsheets of the graph.
Yes.
So,
And this is not very difficult. What is the set of vertices in general? So the set of vertices is the set of patterns which has length maybe just one below the maximum length here. Because the vertices represent the memory you have to recall when you read the full configuration to be sure that you don't have any of these patterns.
solution, like 1, and from 1 we can go to 0 or to 1. From 0 we can go only to 0, so there is a loop, and from 1 we can go only
Maybe, but I should remember, so here I should remember that it's 1, 0, and here it's 1, 1.
yes.
And here, because 0, 1 is forbidden. Okay. But yes, in this case I don't need to remember this one. Here also, but here there is no possible way to this one either, but there is a way of continuing like this. And when you have more or less found all the vertices, yes, you have some kind of tree like this, and when you have tried everything and you have some graph like this, and then you can erase, if you are in Z, if you are indexed by Z, you can erase all the vertices without incoming edge. You can always erase those without outgoing edge. And now, but this one has an incoming edge and an outgoing edge. So, is it an empty system or not? No. And how many, what's the entropy?
0.
How many configurations?
Only 1.
And how many periodic configurations?
1.
So, do you agree that it's completely computable to see that whether a system is empty or not? So just compute this graph, and I check how will I finish. At the end, how will I finish to check that there is an infinite path? What's the main remark about finite graphs? If there is an infinite path in a finite graph,
Here the cycle.
yes, it has a cycle. So it means that every non-empty SFT and needs a periodic configuration. So if you give me a local constraint to satisfy, I can either check with a semi algorithm. I can check whether I can go as far as possible when I extend words that don't contain forbidden patterns. And at the same time, I can have a semi algorithm which which tries to find a periodic configuration. Do you more or less understand what I mean by semi-algorithm? I will repeat what I'm saying, maybe. So, a semi-algorithm is something I can write, I can program, and I'm asking a question to it, and if he says yes, then he will eventually, if the answer to my question is yes, then the algorithm will eventually find that it's yes and tell me yes. But if it's no, maybe the algorithm never tells me and just keeps running. That's why it's a semi-algorithm. So, example, you are given a list of forbidden patterns, and is the subshift of finite type empty? There is an obvious semi-algorithm which works even for every dimension, which is, I tried to look at patterns of size n by n, which don't contain any forbidden pattern. Do you agree that I can write an algorithm like this? I look at all patterns of size n by n in Z2, or n in Z, or n by n in Z3. But the important thing is that it grows, and if the system is empty, then by compactness there is one n such that it is empty. So let me write it for Z. So I write for Z, but the reason why I write it more precisely than what we did here, because I think you all got convinced here that we can decide many things.
We have finite number of forbidden patterns.
Yes. The reason I'm writing it is because it will be important for the higher dimensions. Okay. Let me press loops forever. Not empty.
But if we have Z case, we can check, we can write an algorithm. We can construct
Yes,
a method.
yes. Yes. So I'm decomposing two sub-problems. But you're right that we did better here because we had an algorithm which exactly answers. But here, I'm emphasizing this because in dimension 2, it will still be true, this. But in dimension 2, this will not true because we don't have the graph. So, how how do we do this? I just check if I can tile a segment of length m. Avoiding f for every n. So I check if I have at least one letter which avoids forbidden patterns. If yes, then I go to 2 letters. If yes, I go to 3 letters. If I can find a word of length n which avoids all patterns of length f, or in the list f, then I go to n plus 1, etc. So this is a semi-algorithm. And if I cannot fill length n, then my system is empty, because I cannot even find a finite length. But if I can fill for every n a segment of length n, compactness tells me that I have an infinite configuration. But on the other hand, there is a semi-algorithm which, given f, says whether xf contains a periodic configuration. How do I do this? Well, I take something of length n and I imagine that it's the period of a configuration. If I find a configuration of period P which does not involve any pattern from the list F, then I'm happy. I say yes. But if I don't, I try P plus 1. And if I run these 2 semi-algorithms in the same time, then it's nice, because then I know that one of the 2 will eventually say yes, because there is no such SFT which is non-empty and has no periodic configuration. So I can run 2 semi-algorithms at the same time, and one of the 2 says yes. For you, it was already obvious that there was an algorithm, but again, I'm insisting on this because this will not be true in dimension 2, and so we have these 2 semi-algorithms, but you can run them in parallel, but maybe none of the 2 will eventually answer, and then you don't know if you have to wait for more time or it will never answer. Okay. There was also other questions on this.
If we have in case of D2, what is the periodic configuration?
Yes, good question. You have to define it also. But so we will see it. But actually, in every definition, every reasonable definition, this is false. Well, there are basically two definitions. Either there is one vector of periodicity, or maybe two, yes, and
D vector.
Yeah. For SFT in dimension 2, it's equivalent. The two are equivalent. But we'll see this later. Maybe now, either because there was an exercise on entropy, but I think we did 15 minutes. So, any questions on what we saw so far? Or on the exercises?
Interesting question.
Yes?
Is it a proof that there are no algorithms in dimension to check? Like graphs. So is it like a fact or is it just like an assumption? Just don't know the algorithm or
No. No. We know that there is no algorithm,
you know this?
but this is not a proof. This is a proof that this. So we would have. This would be a proof that if we know that there is no algorithm, then we know that there is no periodic configuration in every non-empty SFT. Because if there were, then this gives an algorithm. But yeah. So we will see. So before seeing dimension 2, I would like to see two more classes of one-dimensional subshifts, which are natural. So let me give you an example. If I tell you, you take the set of configurations of infinite words over 0, 1 to the z. Such that there is exactly one. Any remark on this set? Is it so? What kind of questions? What kind of questions do you want? Even if you don't have answers, maybe you can just ask questions which are related to the course. Yes? What?
I mean,
so what kind of set are we interested in this course? For example, is it a subshift? To start with.
No.
It's shift invariant, okay. Is it clear for everyone that this is shift invariant? I'm not speaking about a specific cell.
so zeros are not prohibited.
Zeros,
Yeah. Zeros are not prohibited.
You mean any number of zeros?
Yeah, then there should be 0 there.
Yes, good remark. So, in other words, this set is not closed. Because in the closure, you should have a configuration with all zeros. The way to see it, the way I see it, is you imagine you have your word like this, and you shift it because it's shift invariant. You can shift it, stay in the set, and you shift it to infinity, and then the one goes away, and you have no one. Okay?
I have another exercise, what is interesting. So you have union of two subshifts, shift spaces, which is full shift. First union. Then I want to show that one of them is full, or both.
Yes. So in
Very interesting.
you did it.
No.
So we mentioned it at some point. I think orally I said because we weren't this kind of questions. Can anyone remember? You have a union of two subshifts, which is the full shift. So because I said at some point that a subshift which is not full has empty interior. No, maybe I didn't pronounce this exact sentence, but I said something which was equivalent to this. If you have something which is dense, if you take the other point of view, if you have something which is dense and shift invariant, if you have something which is shift invariant and open, then it is dense. Or empty. I think I said this sentence. Can you see this?
Shift invariant open means dense or
empty, yes. It doesn't mean dense or empty, it implies.
Yes.
We have to be careful with the word. Because you remember that an open set should include the cylinder. So if I include the cylinders, then on the right and on the left, if the open set is non-empty, it should include a non-trivial cylinder. So on the right and on the left, I have anything. It's really a cylinder, and I have all possible patterns. So it means if it's a subshift, then I cannot forbid any finite pattern because I'm allowing all of them elsewhere. So it's the subshift. So it doesn't matter. Yes. If I don't say, because I said if it's a subshift then it's full. If you don't say it's a full shift, it's yes. So, but it doesn't answer directly your question. Yes, it does because
One complex contains an open substance.
yes.
What is full shift?
Full shift is A to the Z,
Oh, okay.
or some A. Okay.
What was the question? We have union of two full shifts?
Two shifts.
Two shifts. And then?
Two shift space.
And
Union is full shift.
Mm-hmm. So if suppose that none of them is the full shift.
No, the alphabets are can be different.
No, I think that,
No, they are the same.
The same, yes.
Because they are included in the sheet.
And division and full. Then one of them is full shift.
Because, did you finish the argument?
no, because one of them contains the complement of another, and the complement must be open because the subshift is closed. So it contains like...
Exactly. Unless the open set is empty, which means that the first one was the full shift. So, okay, just so, in the last minute, let's go back to here. So here, in order to have something which looks like a subshift, I have to change the definition of my set. What about the set of configurations? So it's that there is at most one. Is it a subshift? At most one. Shift invariant? Yes, shift invariant. By definition, I don't.
It's not closed.
So if it's not closed, maybe you can come up with a sequence which does not converge.
The word is said about 0, 0, 0. I think the zeros talked about that.
Sorry?
We already said about like infinite sequence of zeros.
Yeah. But I changed the definition. In this sequence, there is at most one. At most one, that means either exactly 1 or 0.
It means just that we forbid to one. No.
Okay. At most one occurrence of one.
But if we have the sequence of all sequences that contains only one, it converges to 0 sequence, which is not contained.
No, it contains only.
No, this sequence is in this set. At most one occurrence of one. It's a difficult sentence, but this sentence has at most one occurrence of one because it has none. So it has I thought it was clear because I changed from exactly to at most. So this is a subshift. Do you agree?
Yeah.
Because actually we took the closure of the previous set because there is essentially only one possible sequence that we can take the closure of, and there is only one limit that we can add. This is a subshift, and what can you say about this subshift? Does it?
It's not a subshift of finite.
Why?
Because we forbid all words that contains to one.
To one.
Mm-hmm.
It contains
Number of them.
But subshift can represent many forbidden configurations.
Forbidden families of patterns. Good remark. To find one set of forbidden patterns which is infinite is not enough as a proof that it's a subshift of finite type. Subshift of finite type is just one where you can find one which is finite.
It is obvious that for these
but
patterns we cannot reduce the number to finite.
why? So
You can't drop
any forbidden pattern.
So I agree with you, but to be more formal, in the subshift of finite, to prove that the subshift of finite type.
Suppose we have subshift, it is equivalent subshift of finite type. Then we can the length of all words not bigger than some n.
Yes, that's a good beginning of a proof for non-finite type. Yes, I agree. There is a window length. Okay.
Suppose we
By contradiction. Yes. Okay, but just maybe exercise and to formalize this, and because I want to ask another question which is not very formal. Is it difficult? Is it a complex subshift for you? Is it? I don't know. For example, if you read the configuration from left to, imagine you have infinitely much time, and you read the configuration from left to right, and you want to check that your subshift that your configuration is in this subshift. Does it look complicated or does it look simple? You understand what I mean?
No. Can you say one of them?
So it's not a finite type, but I want you to tell me that it's kind of simple definition in the sense that I don't know if you see it, but
Yes, its complexity is not big.
what do you call complexity?
Complexity or something.
Okay. Yes, there are many notions of complexity, but yes, convergence complexity is very small, it's true. But yes, even a simple notion, I read from left to right the configuration. What do I have to remember? What do I have to have in mind?
Did we encounter one or not?
Position of one.
So is it a complex
It's just like one.
information?
One
Exactly.
bit, one bit.
It's a finite memory.
It's one bit information. Zero if we didn't encounter.
Yes. So anyway, okay. Maybe in any case, I don't need to give you a essay because So in the end, I think we keep the same time because not everyone answered me, and all people who answered me told me yes, Wednesday is very good, but more people told me this than usual people that I see on Wednesdays. But anyway, let's not speak about this anymore, and you will watch the videos if you can't come. And so we keep on Wednesday from 12:30 to 2. Okay? And yes, tell me if there are questions. So maybe it is not so difficult. I think you can do it for tomorrow. But starting really from the definition and starting from the argument that your comrade has started, and the contradiction of having a length of a window. Tomorrow I will give you exercises for next week.